Assalamu alaikum, dear students. Welcome to a nuclear physics. I'm Dr. Pervez Ahmed. So, in today's lectures, we will discuss about one of the basic questions in nuclear physics, uh, which is what holds the nucleus together. It's one of the key questions that people normally asking, and it's that what holds the nucleus together. So, let's start our discussions. So first, we take the example of the hydrogen atoms. So the hydrogen atoms, we basically talk. Normally, we discuss about the Coulomb's force of attractions. That is, we talk about the electromagnetic force. So we say that inside the nucleus, we have the protons, and the proton has a positive charge. That is a charge greater than zero, and we know that in hydrogen atoms we don't have the neutrons. That is, and you know that even if we have other atom of the other isotopes of the hydrogen atoms, so though other isotopes of the hydrogen atoms, it has a neutrons, but in spite of that, you know that neutrons, that there being neutral particles, so their charge, that is q is equal to 0. So what actually it mean? It's mean that it's gonna be the electromagnetic force. If we were to say that it's been the electromagnetic force which is responsible for holding the nucleus together. So what about the neutrons? The neutrons, they are the chargeless particles, which mean that they do not feel the force of attractions or repulsions. It's do not feel the electromagnetic force. In simple words, we can negate the fact that the electromagnetic force being responsible for holding the nucleus together. So what it means that electromagnetic force is not responsible for holding the nucleus together. So the next question is it the gravitational force? I mean, the possibilities. Can we check whether that's the gravitational force, which is responsible for holding the nucleons together inside the nucleus? But you remember, everyone knows that for the smaller size particles, the gravitational force is far too weak. It's very weak for the smaller scale particles. So the closer they get, the more photons in the nucleus should be repelled from each other. And we remembers why we're saying that it be the gravitational force. We remember gravitational force is always attractive in nature. But when we go inside the nucleus, and nucleus, you know that there we say we have the proton. So the closer that they get, the more photons in the nucleus should be repelled from each other. So the force of gravity, there is no concept of repulsions, uh, and the gravitational force. So what in sample words we say that? In sample word we say that it's can't be the gravitational force. So what it mean? It mean that something must serve as the glue to hold the nucleus together. It's the force of the gravity is attractive in nature, but here we saying that inside the nucleus, we say that we are having the proton, and protons they are being positively charged particles. So positively charged particles, they basically repel each other. So it can't be the gravitational force, as because we know that the proton, they are very small scale particles. So for smaller scale particle, the gravitational force, they are far too weak. And furthermore, the gravitational force, it's not repulsive in nature. So the basic idea we have for the force, which is responsible for holding the nucleons inside the nucleus together, should be something like, we should be acting like a glue to hold the nucleus together. So what kind of force it will be? So this kind of the force which hold the nucleons inside the nucleus together is called the strong nuclear force. And this strong nuclear force is strong enough to overcome the electrical Coulomb force at a short distance. So with that, we are being able to answer the questions that the people normally asking, that nucleus normally contain protons, and proton have positive charge. but the neutrons, they are the chargeless particles. So the fact is, electrically, the protons, I mean the same charge, they should repel each other, but we are saying that the nucleus is stable. I mean the repulsions, due to repulsion, we were expecting that nucleus might have not been stable. But here, when we're discussing about the strong force, we are saying that it's the strong force which has been responsible for holding the nucleus, and you come to know that this kind of force can easily overcome the electrical Coulomb force at a short distance. So with this now you have answers that in the presence of this force, I mean the Coulomb repulsive force is very 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 weak. And how much that weak, we compared in the last lecture that if the strength of the strong force is 1, so the strength of the Coulomb force will be equal to 1 over 137. I mean this much, this kind of force is I mean it's weaker than the strong force. So the strong force is basically responsible for holding the nucleus together. In other words, we say that this is the kind of the force which is responsible for the stability of the nucleus, and this kind of the force basically bind the nucleons, which is the neutron and protons, they bind it together in the form of nucleus. Even this is not only bind the neutron and protons inside the nucleus, but it also bind the neutron or the proton itself. You know that later on we will discuss in some of the lecture that neutrons, they are not the fundamental particles. They are being made from the quarks. Neutron has been made from the two down quarks, one up quark. So inside the neutron, this is the force which hold the quarks in the form of the neutron, and this is the force responsible for holding two up and one down quark for making them in the form of the proton. So this is the force that basically bind the nucleons inside the nucleus, and this is the force we say that is hold the nucleus together. So all the forces, as you know that we discussed in the last lectures, all the forces are mediated by the exchange particles. We discussed about a strong nuclear force, and I told you that the particles which carry the strong nuclear force, we call that gluons. Gluons, they're basically the massive particles. We discussed about the nuclear force, and we said that the charge and the neutral boson is basically responsible for carrying the weak nuclear force. And we also discussed that these particles, the boson, they are massive particles. I mean the charge boson and the neutral bosons. We discussed about the electrical and magnetic phenomena, and we said that this is being carried by the particle phonons. You know about the phonons, there's been massless particles. We discussed about the gravity, and we also discussed about the gravity is being carried by the gravitons. Gravitons, they are being postulated to be massless, although no one has yet seen one. I mean, so no one has seen any of the gravitons. The graviton yet has to be discovered. I mean, the scientists, they're working on the discovery of the graviton, but still it's not been discovered. The range, or we can say the extent of the force depend on the mass of the exchange particle that we already discussed. So what it means? It means that which is why the strong and the weak forces are removed from everybody experience, being mediated by the massive particles. I mean that's why I mean in everyday life we are not experience I mean the strong force and the weak force, because the reason is given here, that is because being removed from every experience. Why? Because being mediated by the massive particles. This is why it's not easily observable. And the laymen, I mean, they don't know about the strong force or the weak force. Gravity and the gravity and the electromagnetic forces extend infinitely far. Why? Though we say that it's been weakened with increased distance, and these kind of forces, everybody know about them. Why? Because the particles means which carries these kind of forces, they are being smaller massless particles. So the smaller the particles, the more the force will be observable. So we are not able to observe the particles, observe the strong force or the weak force. Why? Because they are being carried by the massive particle. Everybody can easily observe the force of gravity and the electromagnetic force. Why? Because these kind of forces, they are being carried by the particle, by the massless particle, That's why everybody can experience these kind of the forces. So, what is the strength of the nuclear force? So just like from a very simple example, you can understand that the energy or the strength of the nuclear force. For that, you can take the example just like you can see it here. What actually you do? You have to imagine a nucleon moving inside a cubic potential box of a side length equal to 5 femtometers. This is the box with the side length L, which is 5 femtometer. So if you do the calculations for the lambda for wavelength, lambda is equal to that is 2L divided by n. From that lambda, you can calculate the momentums according to the quantum mechanics, that is equal to Planck constant divided by the wavelength. So the Planck constant, you just put the values, that is n. We are setting it for n is basically a quantum number. So n h car, the wavelength lambda here has a value 2L, is twice the length, is the length twice the length. You know about the energy, the kinetic energy of the particle, which is equal to v square divided by 2m. When if you put the values, that is equal to n square h square divided by 8m l square. So if you consider it in 3 dimensions, you get these equations: n square in x dimension plus n y square n z square into whole h cut square, h square divided by 8 ml square. So now what do you need to do? uh, if you consider this equation in the ground state, so the ground state has at the value of n along the x-axis equal to along the y-axis, and that's equal to along the z-axis, and is all equal to 1. So what actually you need to do, you put this value and the equations we have on the previous slide. So you get the values: E is equal to 3h square divided by 8ml square. So you just put the values for the Planck constants. For the value of m, this is the mass of the particles. This is the proton, the mass of the proton, the mass of the neutrons. We are considering those particles which experience a strong nuclear force. So what actually you get the values for the energy, which is equal to 25 mega electron volt. So this is the energy which is needed by a particle to stay inside the nucleus. This much of the energy is needed by a proton, this much of energy is needed by the neutron to stay inside the nucleus, and this much of the energy and this particular range might be necessary for the nucleus to stay inside the nucleus, that is in the range of the strong nuclear force. As part we discussing about the electrons, so in case of the electron and hydrogen atoms, we know that the energy is equal to minus 13.6 electron volt. So if you compare this amount of the energy, that is 13.6 electron volt, with this much of the energy, which is 25 mega electron volts, is very small. In other words, we can say that the energy for the electron, the energy for the electron revolving in hydrogen atom is very small. That is almost negligible for the energy of the nucleus, for energy of the proton inside the nucleus. This is why it's one of the reasons we can say that. That's one of the basic reasons you say that why electron cannot reside inside the nucleus. So that this much of the energy is being needed to stay inside the nucleus. One of the reasons, though, we have too many other reasons as well. So that's all we have for this lectures. See you with more concepts and many more lectures to come. So till then, bye bye.